Swayam Prabha. Digital India. Educated India.
Okay, dear students, today I'll teach you the signal amplifications for ultrasensitive biosensors. Last class I taught you how to modify the sensor surface with nanomaterials. Now let's use this sensor surface for ultrasensitive detections. So this class is really important for point of care device development because I will let you know the ultrasensitive way modifications of the sensing method, sensing technology. Why it is important, what is ultrasensitive, this keyword you should know first, right? Let's show you what I will cover today. Today mainly I will cover the signal amplifications, and I will let you know that really amplification is necessary and why. So the technique, like we can use the chemical amplifications, we can use different kind of like electrochemical amplifications, those technology I can mention today. And what is the ultrasensitive biosensors? And for this ultrasensitive biosensor development, we need some electrodes. So what electrode we need? Suppose I told you like different nanoparticle modified electrode. Sometimes this nanoparticle modified electrode can be very much conductive, highly conductive. It can cause also some drawback, it can cause us some problem. Why? Because some other reaction, some other side reaction also can happen. So we have to normalize, you have to optimize the sensor surface. Those optimizations method I will let you know. And why we need a optimum sensing surface, that I will teach you today. And redox cycling process, this is the main theme of today's lecture, redox cycling. This can help you the signal amplifications. So what is redox cycling? How we can design the different kind of the redox cycling? How it can help to early stage disease diagnosis? I will show you with a real example. So the main keyword for today's lecture is ultra sensitive. So if you can search this all the keywords also, you will get lots of other report also. So you should know this one, redox cycling and electrochemical. So mainly these lectures I will emphasize on the electrochemical. So why we need the electrochemical? That very first class I told you, no, that electrochemical technique is very much user friendly. It is very cost effective technology, easily we can make the miniaturized sensor, right? That's why I mainly focus on the electrochemical. Let's come the amplifications. So we are always focus on some interesting technology, some new technology, new detections method that can be useful for point of care. So point of care means that near the patient, so that patient can handle by themselves, or it can be no need the expert person, no specialized person don't need, right? So for point of care, we always focus on some new technology that can be useful. So it is very interesting to develop some new technology in this nanobiosensing course. It is very interesting. You will get so many informations here. I will teach you very generic concept, like this way, that way, this way can be developed. Now similar knowledge you can try for other sensor development. So if you can understand like one sensor properly here, this generic concept you can apply for other diagnosis. This is the main important part of this course. This is not like if you learn this is very, suppose one cancer detection, this technology same time can be useful for like the kind of virus detections, or maybe kind of other disease detections, like this generic concept. So that's why it's very interesting to study some new detection protocol to understand, to develop a new ultra sensitive biosensor. Let's show you. So why chemical amplification? Generally people developed a sensing surface with primary antibody. Suppose this is the primary antibody 1, and we immobilize, just to drop the target. And here we are using a redox couple. So, what is redox? That also I will show you in the next slide. So, one redox couple that can help actually signal generation. So, it will release electron, that electron will measure, like based on number of the electron we can get the signal if it is. So, this is a very simple technique, like after adding your target solutions and you are applying some, suppose you are applying some potential like 0.3 volt and you are getting some electron. But there is no any other technology, no other amplification you are using, just very basic method we can try for development of biosensor, but this is a very slow technique, you can say the slow detections. You cannot achieve very ultra sensitive detections here. How we can go for the ultra sensitive then? We can detect, we can take a help from another antibody, that is called a secondary antibody. This is the primary antibody, this is secondary antibody, and this is the target. So, this secondary antibody can be labeled, that I told you last class. It can be labeled with antibody, it can be labeled with like other antibody that conjugated with some gold nanoparticles. Also you can use some enzyme also here as a tag that can react with some chemical. So, for getting a amplifications, generally we are using some chemical. That chemical will reacting with the label and it will form some certain product, and that product will react with this kind of redox couple that act as a mediator and will help the signal amplifications. So, I will teach you more details. So, this is the main theme. See, suppose this is one chemical I am using. So, this chemical will help. Let us remove this. So, very basic part now I will show you. See, suppose you have one S. So, this is a chemical I am using. So, this chemical say is reacting with the label, is form the many P. P means some, from S we are getting some product. This product will reacting with this mediator, or this it is also one chemical, and we are getting the electron. So, here number of the electrons that we are getting from the surface will be much higher than this number of the electron. So, naturally if you are getting here with the see here also one target, here also one target, but with the one target here we are getting one electron, but here 1, 2, 3, 4 product, and they will get release, and maybe here also here we will get almost 4 electron. So, we are amplifying the signal, that is called amplification. So, although you have one target, but you can amplify the signal because of these chemical reactions. So, that is this chemical reaction actually amplifying your reactions. So, we are amplifying basically signal to background ratio. I will come this topic. What is signal to background? See, when so this is your sensor surface, you have the primary antibody. This is your sensor surface ready to detect. Now, when suppose you have two sample solution you have. One is with target, maybe like cancer patient, we took some sample, it has some cancer biomarker, and some sample like normal patient, it does not have any target, it is T0, no target, it is T, it is the with target. So, you add these solutions here, as it does not contain any target. So, naturally there is no antigen or any biomarker. Now, when you add the secondary antibody with label, so it cannot bind here because it does not have any target. And we are actually, after adding the secondary antibody, we are washing the surface. So, as you do not have the target, so naturally secondary antibody is not binding. So, if you add the substrate in this sensor solution surface, then naturally as you do not have label, means this kind of reaction will not happen. So, you will not get this kind of signal amplification. So, without target you are not getting any signal amplification. So, without target, that is so let us remove this, there is no secondary antibody with label. So, this is the reactions you are getting means here S only, and you have only this mediator, that is ferrocyanide mediator, and with these reactions we are getting only very low number of electron. So, this is called background. This is the background. So, simply we can say background means without target, whatever means electrons we are getting, transfer we are getting on the sensor surface, that is the background. Now let us come to the second solutions with target, right. So, now if you have target, like you have some cancer antigen, right, it will necessarily bind here, then when you add the secondary antibody with level, and see now it is here. So, now if you so it is similar like this. So, we add the substrate, if from product you will get so many electrons. So, naturally you are getting the very high signal you are getting here. So, this is actually called the signal. With target signal, without target is the background. So, S by B, it is this ratio is called signal to background ratio. So, that is why if you want to make the ultrasensitive biosensor, your background should be very low and signal should be very high. Then only you can amplify the signal, and very low number of the target you can detect. Okay. So, if it is close to background, then that is difficult, because they will be almost overlap, signal and background. So, although you have only one target, means one antigen, but still if the signal to background ratio is very high, then easily naturally you can detect them. So, that is why the selections of this kind of chemical also very important. I will show you now next slide how we can select those chemicals. So, naturally this that is why this is a fast electron transfer process, and it is a very fast technique. Okay. This is called amplification. Just now I told like signal to background ratio, no. So, we have to get this value high, this value low, then only we can achieve ultrasensitivity. So, for that we have to choose not highly sensitive your electrode surface. So, we are selecting some electrode where we are modifying some nanomaterial, whatever I taught you in the last few classes. For that you have to select some electrode, and that electrode should be not too much sensitive with other chemical. Other chemical mean when you use some very complex sample like blood, some complex sample or urine, they contain many other species, that is called interfering species. Blood, suppose you are going to detect a cancer marker from blood samples. So, this is your marker from blood, but it also contain blood contain glucose, it cause the uric, it contain uric acid, it also got fructose, galactose, so many things. So, when you are detecting some cancer marker and you are applying some potential, suppose 0.3 volt you are applying here. So, other species they are also getting the same potential they are getting, and they also can oxidize also surface, they also can generate some electron and they can generate the current. Then naturally they are actually contributing to your signal, then actually your signal then getting some current from this kind of species, that is called interfering species. So, basically your background current actually increasing. See your electrode, A means some interfering species like uric acid, ascorbic acid, glucose, they can also oxidize. O2, your sample contain also dissolve oxygen, they also can take part, they can release the electron. So, they cause some extra background. So, if you want to get the high signal to background, so your background should be low, but your other interference species as I mentioned like ascorbic acid, glucose, they if they cause, then this value will increase, natural S by B value then will decrease, your sensor will not be ultrasensitive. So, for that you can choose some less sensitive electrode towards those interfering species, so that they should react very slow. You cannot avoid basically totally 100% cannot avoid them, but you can decrease their oxidation on the sensor surface, even almost tends to 0 you can make them. But you have to select a electrode so that your main reaction that I taught you last class, last slide, like your last slide I taught you, no, like by using secondary antibody and label, so substrate will react with your label will form the product, and that will generate the electron that we can measure. So this is very specific reaction actually. These reactions we can measure, and this is signal, and this should be very high. This S should be very high, then background. So if we use some less sensitive electrodes towards the interfering species, but your signal should not be hampered, it should be high, and we can get very high signal to background, and we can achieve the ultra sensitivity. Clear? Now next slide I will teach you how this part, like chemical reaction part, easily we can design and we can get the high reaction. I mean we are getting fast reactions, because this part is important also. Signal part is important. We have to focus here. But while we are focusing signal, at the same time we will take care of the side reactions, so that like other side reactions should be low. I will show you next slide now. So these all the background reactions should be low. This should you should keep in mind, so that you get a slow reactions with background and fast reactions with your expected reactions. Okay. Now I will come to the redox cycling. What is redox cycling? That can help the signal amplifications. So redox cyclings, it is the two reactions. One is the redox, means red means reduction, ox means oxidation. So you know reductions means we have to provide some electron, right, and oxidations means it will release electron. You can see this step, Fe2 plus, Fe2 plus means this ion we can get potassium ferrocyanide K4 FeCN whole 6. So we just mention Fe2 plus here, oxidation state iron 2. So it is actually Fe2 plus. So that I just put the Fe2 plus. So if we mention Fe2 plus, it means like similar like this, some mediator, or it is a complex, iron complex. And Fe3 plus means K3 FeCN 6. Here iron oxidation state 3. It is Fe3 plus. Okay. See, if it released one electron, then it will form Fe3 plus. So it means it is the oxidation, say one electron releasing. So when next slide I will say oxidation, so you should keep in mind that one electron it is releasing. Now if you give one electron, then Fe3 plus will form the Fe2 plus. So this oxidations and reductions, we can make it cyclically on the sensor surface, not only one redox. I mean here is just for example iron, we can make many redox couple on the sensor surface, and they can react each other like this way. They can react each other like 1 cycle, 2 cycle, 3 cycle, they can form on the sensor surface. If you sensor surface like this way, like like 2 or 3 cycle if we can make, so then so one substrate can take part. So this electron transfer will be very fast on the sensor surface if there is a discoloring of redox cycling happen. But if the sensor surface only one redox cycling from substrate, this electron transfer, if we compare with the here electron transfer, suppose here kinetics, if you mention here kinetics 1, here kinetics 2, this K1 will be very high than the K2. So that is why now we will focus on how we can make this kind of a redox cycle on the biosensor surface, so that we can amplify the signal and we can achieve ultrasensitive biosensor. Okay, so just now I told oxidations and reductions. Now I will come a real example with redox cycling. I think this part I already taught you last few slides. You have a primary antibody. This is primary antibody on the sensor surface, that is avidin coated I2 electrode. That is the biofunctionalization I already taught. This is the primary antibody and avidin, and this primary antibody already conjugated with biotin. iodine, biodine, they have strong interaction. Like this way, I form a sensor surface. Clear? So, this sensor surface is ready for CA125 detection. This is a cancer antigen. Just for example, a cancer antigen I want to detect. So, I have to use a specific cancer antibody. So, generally I will tell you the brief procedure how we are developing this kind of sandwich biosensor on the sensor surface. So, up to this your sensor surface is up to primary antibody, your sensor surface is ready for detections. Now, we will draw your target solutions. So, if it has target, then it will bind, and then we will wash the surface, because there is some other places where there is no antibody, but target still may be there. We have to clean them, otherwise the secondary antibody also can bind here and there, because it is the specific site, but other portion is the non-specific site. So, two terms come here, one is specific binding, another is non-specific binding. So, what is specific binding? Specific binding means this is the like the antigen antibody binding here, this is the specific binding. So, if antigen there, then this secondary antibody it will bind here. So, we need these portions, because this is the expected your part. But sometime when you add the secondary antibody that is conjugated with some tag or label, suppose here glucose oxidase on enzyme, we tagged it the secondary antibody, and it also can bind here also sometime. It should bind with the target, but sometime there may be some your surface may behave such a way they can attract your secondary antibody that is conjugated, but that is not expected. Why? Because as it is tagged, it also can react with some chemical, it will form the like a signal. Means you should get the signal once you have the target, but see here there is no target, but still if the secondary present, then you will get the signal, because they can increase the background current. So, this is actually non-specific binding, and non-specific binding can increase the background current. You do not have target, still secondary antibody binding. That is why after adding the secondary antibody, you have to wash the surface very carefully, otherwise secondary antibody also can be here and there, and they can react with the substrate. It can generate the electron or current that is actually can it can't count with the signal. So, we have to be very careful. That is why. How we can be careful? Means this is how we can avoid the non-specific binding. Then we can very carefully clean the surface after adding the secondary antibody, so that it should bind only here, because they have the strong interaction, they can easily bind. But this non-specific binding is very loosely bind, this one. So, we can easily remove them by washing. Otherwise, see there is some bare surface, this bare surface sometime can help to bind this non-specific binding. So, that bare part we can add some small protein molecule, that is called BSA, bovine serum albumin, the small protein molecule. If we can cover the surface, then they actually will hinder not to bind this kind of secondary antibody on the surface. So, we can avoid the non-specific binding. Okay. So, I just told you that like this way we can form a sandwich method on the sensor surface. Now, we can add here some substrate. So, okay. So, now I will show you the actual redox cycling reactions. So, let us remove the basic part of the sensor formation now. Now, I will show you only chemical amplification. So, how we can amplify. Okay. So, I will add some substrate. So, here substrate is the glucose. So, glucose will react with the glucose oxidase, it will form the gluconic acid. So, here actually electrons we are getting glucose oxidase as a level, it is also catalyst, and this will help to oxidize the glucose, and we will use some mediator. As I told last time, I used the iron based, here I use the ruthenium based mediator. Why it is mediator? Because it will help to take the electron from glucose that oxidize on the glucose oxidase, and it will form ruthenium 3 plus, ruthenium hexamine 3 plus to ruthenium hexamine 2 plus. So, it will reduce because this electron we are getting from glucose and it will oxidize glucose oxidase, it will help to transfer the electron. So, this reaction happen. Basically, this is what? It is getting one electron, right. So, this is the reduction. So, then we can apply some potential on the sensor surface, so that we can oxidize it, because we have to form a cycle. So, we can oxidize, suppose we are applying here as a 0.3 volt we are applying. So, it can oxidize, it can release the electron. So, again it will form the ruthenium 3 plus. So, this ruthenium 3 plus again it will get the electron from glucose after oxidizing on glucose oxidase. So, this cycle reaction happen again and again on the sensor surface. So, this reactions is happening again and again, and it shows ruthenium hexamine 3 to 2, 2 to 3. So, kind of it is reproducing. So, redox cycling basically helping to make the kinetics faster by reproducing the mediator on the sensor surface, clear, and you will get the faster electron transfer. So, this is the mediator, and just now you can understand here in this sensor surface what is the starting material. So, we are using glucose and we are using ruthenium hexamine 3 plus. These two is the starting material for this kind of signal amplification strategy. See, if you just think, if you have target, then only glucose oxidase will be there, right. If you do not have target, there is no glucose oxidase, right. And if glucose oxidase present, then only glucose will oxidize, and then only ruthenium hexamine 3 plus will form the ruthenium hexamine 2 plus. So, you are using glucose and ruthenium hexamine 3 plus. So, to generate the high signal to background ratio, your glucose and ruthenium hexamine 3 plus should not react to each other. There should not be any chemical reaction or very slow chemical reactions, because they are starting reagent. They will produce the background current. So, if there is no target, like there is no target, so only this and this will be present because there is no glucose oxidase. Ruthenium hexamine 2 plus also cannot form because they are not getting electron. So, and ruthenium hexamine 3 plus, because it is already oxidized form. If we want to oxidize it again, ruthenium hexamine 4 plus is not stable much. We cannot make the faster reactions. That is why background will be very, very slow. So, we have to choose such a mediator in the higher oxidation state, so that it will not react very fast on the electrode surface. So, you naturally will get the low background. And when target present, right, you have the CO125 target, then it will bind with the secondary anti-glucose oxidase and glucose will react. Then ruthenium hexamine 3 plus immediately transform to a ruthenium hexamine 2. Now, this reduced form should be highly reactive on the surface when we apply some potential. This is the electrochemical reaction. On the electrode surface, we are applying some potential and it is highly active and it will release the electron. So, this part is the electrochemical part, electrochemical reaction. Okay. This part electrochemical reaction, and this part it is actually enzymatic reaction. See, glucose reacting on the glucose oxidase enzyme form the gluconic acid, release the electron. But it is kind of chemical reaction, but as we are using enzyme, that is why we are saying it is an enzymatic reaction. So, we can put some nomenclature in this kind of reaction. So, here it is a redox cycling reactions, but electrochemical reaction, electrochemical redox cycling, and this part enzymatic. So, we can put a name. So, this is a redox cycling happening here. So, we can put a name enzymatic redox cycling, because here enzymatic reaction and here some redox cycling electrochemical. So, we can mention also it is electrochemical enzymatic redox cycling, electrochemical enzymatic redox cycling. It has a one abbreviation, we are saying it is EN, EN we can mention. So, let us clear this concept today. Next class I will bring again more redox cycling. This is just one example. This is one example I taught you today, like enzymatic redox cycling. So, we can add some redox cycling procedure to amplify the signal, and for that we have to use a mediator and we have to use some starting reagent, some substrate. So, here in this case glucose. So, your glucose and ruthenium 3 plus is the starting material, and they should not react each other very fast. And also ruthenium 3 plus glucose, this mixture also should not electrochemically, when we apply some potential on the surface, they should not react fast, so that we will get very low background. Okay. So, background part clear. So, we will get less current here. Now, when we will add the target, then you will get actually your label, your tag, your catalyst, then your substrate will react with this, then your mediator will start reactions, and they should be highly active on the electrode surface when you apply some potential. Then redox cycling will form and we will get very high current. Just keep in mind, in the presence of target it should be, so that we will get the very high signal. So, naturally your signal to background ratio will be very high, and this will be a very highly sensitive biosensor. This is just one example. Next class I will teach you again like different kind of redox cycling. This is EN. Now I will change the tag, we will incorporate some many other chemical, and why I choose ruthenium here, why not any other mediator. So, we can incorporate many mediators also, that last slide I taught you, know. So, like 2 or 3 cycle also make to make the reaction much faster to get high signal, that also possible. So, that things I will teach you in the next class. So, this is the different redox cycling that I will teach you, and I will give you more example, like we can bring some more tag, not only the glucose oxidase, we can make some other label based on nanoparticle, that I will teach you in the next class. Okay. So, this is the things, sorry. So, this is the conclusions part. The main conclusions here, that nanoparticles can be useful for biosensor development, and we can functionalize the surface, and we can use this kind of fabrication technology by using some extra chemical for development a ultra sensitive biosensors. Okay. So, let us wait for the next class again. I will teach you some more technology for getting the ultra sensitive biosensor. Thank you all.